Hello everyone. Today this is the lecture number 10 in the series of fluid mechanics. So in this lecture we are going to discuss about vapor pressure. Okay. So we'll see in the first chapter of the fluid mechanics we are discussing every topics not in detail but just I'm just introducing every topics or the every concept or the every term so that when we move to the actual concept or the mathematical part of the fluid mechanics we do not feel isolated, right? If you don't know any concept you don't feel isolated. Okay, so that's why I'm discussing every concept after videos. So don't feel like the course is in a very discrete form, like discrete form. In the previous lecture we have talked about surface tension. Now we're talking about vapor pressure. Again we will talk about something else. So just I'm just make sure that all the concept have to be taught here, so that in the upcoming lectures in the next chapters, from the next chapters we will discuss about the core concept or the mathematical things of the fluid mechanics. So in those lectures we will directly discuss about the vapor pressure. We are not going to discuss everything about vapor pressure, the basic things. We will just just use the term vapor pressure, and you are predetermined, like that you people are know about that. Okay, that's why I'm discussing here in discrete format. Okay, so let's discuss vapor pressure quickly. So what's the vapor pressure, right? So vapor pressure is a pressure at which liquid boils and is in equilibrium with its own vapor. Okay, so that means whenever the liquid boils and for instance, pressure of the liquid part of the fluid and the pressure of the gaseous part of the fluid, when both become equilibrium, then that condition is known as, the pressure at which this both become equal, then that is known as vapor pressure, right? And this should be equal to PV. Okay, so for any fluid, when the pressure of the liquid and pressure of the gas become equal, then it is known as vapor pressure, right? For example, when you start heating the water, it usually boils at 100 degrees Celsius, right? So it's boils at 100 degrees Celsius. The water in the liquid, the water that is in the liquid phase and the water that is in the gaseous phase, both the pressure having equal. Okay, that means vapor pressure of the water is 1 atm, right? The gaseous pressure over the water is 1 atm, right? And the liquid water should have to pressure equal to gaseous, and at that point then the pressure is known as vapor pressure, right? And at that point the water starts to boil. Okay, now let's see, we have seen that when both are equal, then that is known as vapor pressure. What will happen if pressure of liquid is greater than pressure of gaseous? Okay, if that is the case, then we will call it as evaporation, right? The case of evaporation. So the exchange between the fluid and the liquid and the gas is only evaporation. Okay, at the interface, evaporation at the interface. Okay, so if you have studied evaporation in your school days, you have learned that when the water is not at the 100 degrees Celsius, even though the water starts evaporating, right? The water is getting lost in the atmosphere, right? So in that case the pressure of the water is greater than the pressure of the gases. That means the pressure inside the water is larger than atmospheric pressure, right? And that case, that interaction between the fluid and liquid, or the exchange between the liquid and fluid, that is known as evaporation, right? Okay, so the second case can be when pressure of liquid is lesser than pressure of gaseous, right? So in this case, okay, so this is known as when the liquid pressure falls below the vapor pressure. So this is, we call it as a cavitation. So why we call it a cavitation means, what do you mean by cavitation means? Bubbles, air bubbles. Actually, air bubbles can be found out in liquid. Okay, so what I mean to say, let's suppose one pipe is there, right? one pipe is moving, okay, and some water is there. It's not working. Yeah, okay. So let's suppose some water is flowing here, okay, inside this pipe, and you will see that when again uh, okay, so when water is flowing here, and if you see any bubble forming inside the water, I mean this bubble, inside this bubble air is there, right? So at the interface both liquid and pressure are having, and when the liquid pressure is lesser than the gaseous, that means this bubble will not burst out, right? So that is known as cavitation, okay. You will see these conditions in practical cases, right? That cavitation will form in the pipe or something, okay. So this can be seen when the water is ulcerated from rest to about 14.2 meter per second. Its pressure drops about 101 kPa or 1 atm, right? So I mean the atmospheric pressure is 1 atm, okay. And when water is flowing, I mean it is ulcerating at very large ulceration. Let's suppose it is actually it's happening at 14.2 meter per second, okay. This can be found out from experimental data, right? And when it's flowing with this ulceration, the pressure inside the water falls down with below the atmospheric pressure, right? And in that cases the cavitation can occur, okay. So I mean, see, the dimensionless parameter describing flow induced boiling is cavitation number, okay. So that means when flow is happening, and for the flow, whether the flow will boiling will occur or not, that will defined by cavitation number, okay. So what's the cavitation number? How it's defined is I am writing here cavitation number, okay. So it's like a kind of non-dimensional number, and it is Ca equal to Pa minus Pb upon half rho v square, okay. So I mean if flow is moving with the velocity v is the velocity of the flow, okay. V, rho is the density of the flow, Pa is the ambient pressure, ambient or atmospheric pressure, okay. Ambient or atmospheric pressure, okay. And Pb is vapor pressure of the fluid, vapor pressure of fluid, okay. And this V is characteristic velocity, not a simple velocity, right? We have discussed earlier that characteristic distance and characteristic velocity are two different things, okay. And we will see how we will find out for different prognosis, okay. It will vary according to geometry and kind of things, okay. And what is the fluid density, okay. So this cavitation number will tell describing the whether the fluid is flowing, and if boiling is occurring or not, that will be defined by this cavitation number, okay. Or for designing any pipe, like for any oil transportation or water transportation or gas transportation, a pipe has to be built, right? During that, engineers have to calculate this cavitation number so that cavitation can be provoked after that, making this pipeline, so that this cavitation will not occur in this pipe. So according to that, cavitation number has to be assigned, okay. And the dimension or the fluid, the pressure has to be designed, okay. Dimension or the design of the pipe has to be done, okay. So depending on the geometry, a given flow has a critical value of Ca, right, below which the value will begin to cavitate, okay. So before designing this pipe, okay, so for any particular design, Ca could be differ, okay. If Ca is lesser than critical value, okay, then it can cause cavitation in pipe, okay. Now the question comes in your mind, like what's this critical value, sir? How will we find out? So this can be found out from the different geometries, okay. So for different geometry, the table has been made. So it's many standard institution made their own table, and according to that critical values vary, okay. So it can vary from geometry to geometry, and according to that you have to assign the critical you will find out the critical value, and your cavitation number should be lesser than that, greater than that. If it's lesser than that, then the fluid begin to cavitate, okay. And that cavitation in the pipe can collapse the pipe, or it can rapidly spoil or erode metallic surfaces and eventually destroy them. Okay, so these are means this cavitation number is very critical parameters to observe about it. Okay, so this is all about vapor pressure. Just I have to discuss it shortly. Okay, so in next lecture we will discuss about boundary condition, sleep condition, no sleep condition. Many of you may know, but we will discuss in detail in the next lecture. Okay, so till then keep learning, and goodbye.